figure out right away how many pieces there are. Just see what things can be connected. So that's obviously connected. Now that has, there are other features of cohesion. This will suffice to show the contrast, because if instead I take the irreflexive volume and not necessarily reflexive, then this is the Precious on a category that has no compositions in it. It's got two objects and two arrows, but they're parallel, so there's no non-trivial compositions to be done. I mean, this looks like a graph, but it's also a category automatically because of the trivial way things connect up. So now, first of all, an object, previously we could say that an object is one set, among whose points are the fixed points, so that's the second set. You see, so there are really two sets there, but one is sort of in this case we have to say that it's two sets. So an object X consists of two sets, X1 and X0, and again, two arrows that we could call source and target. So the picture of a graph, now here the picturing gets tricky because the conventions for the picture are different. Here, a dot is an arrow, namely a degenerate arrow. Here there are no degenerate arrows. They're just dots, which is a separate thing. A loop, of course, is an element of X1 that goes to the same place under these two arrows. So some dots have loops, but some dots have no loops. In any case, there's no designated loop. Here there's a designated loop given by the canonical degeneracy. So when we talk about morphisms, of course, as always are natural transformations. Morphism in this category is a pair of maps of an S that make two commutative squares like that. And here a morphism can degenerate things. It can collapse an arrow to a trivial, to a degenerate, i.e. to a dot. Here, you could degenerate an arrow to a loop. If there was a loop to degenerate it to, there might not be any. Or I might not have any loops at all as an extreme case. In which case, all these maps would be monomorphisms, by the way. One of the things that can map to the anti-reflexive graphs are subgraphs of it. You get a person. Something I hadn't realized until yesterday. Anyway, all right. So what is the point now? Since you don't have the reflexivity as a structure, therefore morphisms need not. There is no designated loop. If you tried to designate a loop, it wouldn't help because it might not be preserved by morphism. You have to change categories. I have great problems reading books on graph theory, books and papers on graph theory, because they never tell you exactly what they're talking about. Sometimes the graphs are universal, sometimes they're reflexive, sometimes they're not, so even though they go so far as to talk about homomorphisms, I still don't know exactly what that is, which category are we in. What they should do is admit that they're working in 3 or 4 different categories, if you know how to pass from one to the other, and so on. It would simplify everything. But no, they prefer to talk in a vague way, sort of smushing these together. And they're actually trying to understand some of the problems of graph theorists, and I get blocked from the first page if I was like that. Does anybody actually know what a graph minor is? Graph minor. Big problem. I mean, the guy who's the head of the International Mathematical Union, who's also a big shot with Bill Gates, he promotes this problem. He's famous for working on this problem, on graph minor. It looks like it might be interesting. But I can't determine exactly what it is, because if you read the first parts of the paper, they waffle, you see. And they don't give you a property. They say, well, you could remove this kind of an edge and put back in that kind of an edge, and talk about a finite number of sequence of steps of that sort would give you the kind of thing we have in mind. But you don't know what kind of thing we have in mind. Now, of course, such a calculational test would be a great thing for a concept that was clear. But it's very hard to have a clear concept that is only that as a so-called definition. You see my problem? Anyway, the basic point is that there are at least 3 or 4 kinds of things called graphs, really 3 or 4 different toposes that are all closely related. They have apparently slightly different properties, but what I'm emphasizing here is they have radically different properties, because this one is a cohesive and not variable set. Because let's take, now here again you have the generic figure, but actually you need 2. You see, there's just a bare dot is one figure shape, and an arrow is the other. And this arrow means, though, something different than it meant here, because this thing has really only one arrow and 2 dots. Whereas the basic figure for the reflexive case, it has 3 arrows. It's just the 2 of them are degenerate. So it behaves pretty different. What if I take the Cartesian product of this with itself? It still has, by itself, it still just has one component. One component. Again, it's obvious whether the thing is connected or not just by looking. Well, okay. This is, I said, what did I say? This has 2 dots, and therefore the product has 4 dots, just as before. But how many arrows? An arrow is an ordered pair of arrows. There's only one arrow in each. So there's only one arrow in the answer. And of course it's this one. Pasta. That's the whole product. Which clearly has 3 components. Not 1. 1 times 1, not equal to 3. And therefore that action is not satisfied. Now that's a very, very important axiom. Well, as we'll see later, for various reasons why it's very important, but this shows clearly. Now the other thing was, as I was trying to explain in words without pictures before, is that not only do we have these abstract properties, which is different, but this one concretely can be seen as a variable set, because, shall I call this A again? Ensure confusion. Well, let me say there's this general thing that if you look at presheaves on any category C, and suppose X is a particular presheaf, then the slice category, I mean the one which consists of all figures in X of arbitrary shape, that's actually itself again a presheaf category. Namely, the exponent is figures of shape C only. I mean, of shapes in C. That's a basic formula in thinking about these things. So, in this case, what I want to do, I want to say that this is locally poset. So, if I take the category of non-irreflective graphs, slice it again by the generic figure, which is the arrow. This is actually just presheaves on this category. And if you figure out what it is, you have to calculate all the commutative triangles and so forth and so on, and see that what it really reduces to is this poset. Poset. That's the whole thing. After having sliced, even though double arrow is not a poset, this is a poset. This is a poset. That's actually characteristic of the small category C consists of epics, like in Johnston's QD adequately separable things. If you slice, now in general you can take the sum of all the objects in C, that's a single object in the topos, and slice by that, you get a poset. So that's really the idea of these everything being epimorphic, that if you sort of look at the category of figures, geometrical figures of those shapes in something, it becomes, because of the cancellation. It makes 30 micrometers. cancellation, the definition of epimorphism says that two maps are equal provided we compose them with one first. But when you pass to this category of incidence relations, that's already saying any map there is composed with something. So therefore, the maps are actually unique. What?
I think you have to take them like seriously. At least not.
You mean I have to talk to it or fight it? What? So this is what you get, okay? Now, this is the picture of the basic, of the open sets. Did I do that right? I'll get it wrong, backwards. This post set can be realized concretely, as I said, this way, that you have a 3-point space. I suggested even that you could think of it this way, that you collapse this whole open set to one of them, this whole open set to the other one. It sort of explains why this space, trivial though it looks, is going to come up a lot, because you have to make decisions. Is it greater, equal, or less? Of course, even that's not the only interpretation, but this is one equal interpretation of this set. So now the thing is that I want, these 2 points are open. There are 5 open sets altogether, because there's the whole thing, there's the union of the two, as well as each one, and the empty set. That makes 5. But really, it's all determined by 2 open sets. The axiom that says they are disjoint. I think of it as a presentation of a distributed lattice. 2 generators with the one axiom that their intersection is empty. And it has these 5 elements. And this other point, which is not open, but it does mean that the whole space is different from the union of the 2. Top, so this is the top element. This stands for the whole space. This stands for one of the open points. This stands for the other open point. And these are the inclusions. So the 2 open points are included in it. So a sheaf on this space, what's a sheaf? Well, in principle, it's a set assigned to every one of the 5 open sets, together with restriction maps. But on the other hand, there's a pasting condition, which means really I only had to know the sets assigned to those 2. And that's without any condition. So it's an arbitrary pre-sheaf on this diagram. For my conclusion, I wouldn't need it to be arbitrary, but it happens to be. So in other words, basically the graph is a variable set along this post set, except that we require that these 2 sets be the same. Namely, that the arrows are not the same. It's a kind of a quotient, see, of something which is an ordinary topological space, namely this one. We take but we think of this as a topos instead of as a space, and so we take the quotient in the larger world of toposes, just identifying, merging those 2 open sets without merging the inclusion maps. You get something which is no longer a closed set. And that's why it's in a very strong sense, a variable set, because not only does the site not have any idempotence, every map is about both epi and mono, so we have the intersection of the 2 and the union. Actually, I think there are 5 things there. No, but the non-typical intersection.